Okay, Norm, he likes the, and I agree, I think the optical interconnect, that Google, of course, I'm biased because I get a paycheck from Google, but I think the optical interconnect is a very cool feature. What about the NVIDIA architecture do you find attractive? or the customer base?
I think Bill said it well, in that, you know, there are certain operations that we both have to support, you know, matrix multiply, vector operations. One of the things that was different about TPUs is, I mean, our first one was a PCI card, and just an inference, but starting with the second one, they were designed to be supercomputers. So we have the Taurus network as in Bill's book with Brian. And so we didn't have any painful steps along the way of adding features and having other features kind of conflict with those features and stuff. So we were able to start out with a clean sheet of paper with a supercomputer design.
Yeah, I think that was impressive. The fact that your second design in 2017, you realized that you needed a supercomputer for training, and yeah, that's what you were going to build right from the start.
Yeah.
And it was either, it was liquid cooled in 2018 or something?
Yeah, so we've been liquid cooled for 8 years.
Yeah, so, and that's what the levels look like. Okay. And by the way, I'd like to thank the people at Hot Chips, which happened right here. So we got a couple days ago, I went around and asked for questions to give Bill. And so we got some really good ones. Okay. NVIDIA and Google are both world-class system companies. Has the engineering of systems, the interconnect, the memory, power, cooling, and packaging become an even bigger moat for the competitors than the silicon itself? And how do your approaches to interconnectivity address the critical bottlenecks and scaling? Where are they similar and different? I think, Bill, it's your turn to go first.
Okay, so I think the product is the whole system. That's not just the GPU or even the board with GPUs, CPUs, and networking gear. It's all the hardware, all the software, and the configuration that makes them all work well together. Starting, I think, in our Pascal generation, I think it was about 2015, we started offering something we called a DGX SuperPod, which was, if you bought, this is even before we had all the captive large-scale network. We had our own internal, link networking, but we then acquired non-ops. But you use this switch, you would configure it like this, and you do that. If you did that, you could put together, a collection of, in that period of time, maybe 10,000 GPUs, and you would turn it on and it would work. But in contrast, when we would build the big DOE supercomputers, like when we did Titan in 2011 or 2012, and Summit and Sierra, you would typically go through a 6-month period after you had all the hardware working, bringing it up because of little things in network configuration of different things. So you're delivering the entire product, you're delivering a system that has to work reliably over long training belts with very high availability. And so, I think there's a lot of systems expertise that goes into delivering that, having a standardized configuration. For us, because we're selling into a lot of different data centers, and people did things different ways, it was critical to get the system up and running quickly and run it extremely reliably. Now, where things different, I think our scale-up network is probably the place that our systems that are the most different. Google uses the 3D torch with the optical circuit switches to figure out bad things. We take a much more conventional network approach, where we basically build our scale-up network with a flow network, proprietary variable latency link to get around a lot of the overhead conventional Ethernet, and then have a scale-out network that is conventional.
Yeah, and just following up on one of your points, I think a lot of the startups don't have that system experience, and Louise and others wrote, the data centers and computer, and learning about systems the hard way by building the supercomputers. I think a lot of those lessons aren't obvious until you've experienced the pain yourself, and I think that gives both of us an advantage over startups.
Yeah, you talk about Luis Barroso in her proposal, in Partha's book, The Warehouse is the Computer, something like that. Yeah, it's in several editions. It's all the
Warehouse
lessons,
computing.
warehouse computing, all the lessons that have been learned over the years about building at this giant scale.
Yeah.
So it sounds like, if the answer to the question was kind of, yeah, it kind of is a moat. You don't, the chips, there's a lot more to it than chips. So how much of NVIDIA's and Google's competitive advantage today is really about the hardware versus the software and the compiler libraries? And how does that work within your organizations? And then putting it differently, if you gave the startup the netlist and maybe layout, but not the stack, could they compete? And Lauren, take you.
In the design of TPUs, we try to follow the advice of my thesis advisor.
Well, that's a wonderful idea. I think that should be a requirement. But and what was his advice?
Don't put it off until runtime when you can do it compile time.
Okay.
So we try to do that, and we design the architecture, in a room of 10 people, and 2 of them were part of the department. So we try to make a machine that was easy to compile to, and so I think that provided a lot of benefits. And also, we kept the same general architecture, and this, for example, the sizes of the memories can increase or decrease, and things like that. But that's like having a PC. You can put more digits in your PC and still run, Word. So it's pretty flexible.
What about the libraries?
Yeah, there's a lot of frameworks, and they're evolving. So it's important to keep up with those and with support. And then also, some people like writing their own kernels, and so you need to support those as well.
How do you feel about hardware and software?
Yeah, so, the product is the whole system, which includes, hardware and software. And software is a really integral part of it. But in many ways, for deep learning, it's an easier problem than the problem we had with general GPU computing that sort of led up to that. When we sort of kicked off GPU computing with CUDA and the being launched in 2006, there were literally, thousands of applications that would benefit from running parallel.
Right, guys, so that was a small conference, or a big conference actually, about the use of AI chips, so hardware versus software. Thanks, Diamond. And so unfortunately we are not allowed to to film, interact with the people. So I will link the video of the of the conference here. They are covering it. Most probably, yeah. But I think it's okay. I will just write the link of the conference in the description below, and then people can follow it. So basically, there are 2 people who are speaking. So the first one is from NVIDIA, and the second one is from Google, and they are building chips, both of them. So basically, Google is a software company, and NVIDIA is a hardware company. And the question is, why don't Google use simply the hardware from NVIDIA? Why do Google has to make its own chip? So this is like open debate, and it is like answering it. So let me come back to the conference.
That's a polyanalytic view of what's going on.
I think, any software mode, I think there's still an advantage having libraries that have been tuned and honed over the years that are easy for people to apply. But I think that mode has been significantly degraded because if you have the spec of that library, I think turning, quad codes and recreating it is not that difficult a thing to do.
Yeah, I agree that the mode is getting shelved.
It's getting filled up with sand. Starting to get the water across it. Okay, Bill brought this up, but and Bill is a talk, he gives credit to this. We squeezed a lot of speed and inertia use by reducing precision. Yet, like for me, I shocked it, our exponent is bigger than the fraction. That's a new thing, a relatively new idea. But we can only go so low. What happens for generation over generation improvements when we can't shade bits off anymore?
Okay.
Bill,
we've pretty much hit 2x per year over the past 14 years, starting with Kepler 2012, which is the first generation since we really looked at this as a serious application. And only 3x of that has come from process technologies, in contrast to the microprocessor heydays of the 90s, but it all came from process technology. And I think in NVIDIA we kind of led the way with numerics, going from starting out with FP32, because that's what we had in Kepler, and shipping in the FP4, there's new things in Vera Rubin. And clearly there's a couple more terms that we're getting near the end on numerics. There's still a couple of other things that can be done, but there are a lot of other axes that we can continue to innovate along: sparsity, circuits, locality, even better models that letting people use for more tokens for a lot. But we are sort of getting down to the point where all the low-hanging fruit has been picked. We need to climb higher up the tree to find those 2x fruits hanging from the branches. But we have a bunch of good ideas that could exist for at least the next 4 or 5 generations, and then I can retire.
Yeah, I didn't.
Is that 4 or 5 years? Or 8 to 10 years?
Yeah, I didn't want to suggest that numerics was the only thing. That was one of the. That was certainly a little hanging fruit, right? It's not a bad.
Very low hanging. Yeah.
And we also had some numeric innovation. So when Jeff was doing those initial AI things,
This is Jeff Dean.
They were doing it in FP32, but then storing it by truncating the low order 16 bits. And if you hear truncation and you're a numerical analyst, it's kind of like fingernails on the saw. But it actually worked. So when we developed TPUs, we could run programs in BF16 that had run on CPUs, which were being used at the time.
BF16 is the whacked, the chopped IEEE 32-bit one.
Right. Yeah. So we could run those and get the same results. And so that was really powerful because we didn't have to spend a lot of time debugging things, at the system level. Why is this not working? Things like that. So we could verify correct operation. And then once we had that, we used that for a while before we started adopting the smaller formats like FP8 and FP4.
So I think one of Google's advantages, theoretical advantages at least, is Google both have people pushing the state of AI and building hardware. And so theoretically, that's a big advantage. And I think I read that NVIDIA is going to build up in-house expertise. So what do you think, how big of an advantage is the access to people pushing to the state of the art versus people who are just going to use open models and do that, or, not have that close relationship for now? I think you're right.
Yeah, there's, leaderboards that show, some of the open models are performing quite well. And so there's a race for the proprietary models to stay ahead. I think they'll, do to the ability to do better tuning of the models for a particular system, either GPU or TPU. There'll always be some advantage to the proprietary versions, but
I was thinking more of, as hardware people, could we go talk to the ML people about what's happening next and what we put in our hardware, that if you didn't have access to those experts, you would have to guess. You see that?
to some extent. The problem is it takes, 2.5 or 3 years from an initial idea to have a system that can be manufactured in volume. And ML people come up with a new idea like every 3 months or 6 months.
Okay. All right.
You can't really design for a super specialized, machine for a particular model because it'll be different. And like Bill said earlier, you just have to do those basic operations, matrix operations, vector operations, and stuff, and do them well.
Okay, if it takes so long and they iterate faster, why are you guys getting into building your own models?
We're not getting into it, we've been doing it.
Okay, sorry.
Some time, and we have a lot of internal expertise, but I think there's a distinction here between, a company like OpenAI just had a great paper on hot chips on their jalapeno processor, where they're designing a chip pretty much to run one model. Therefore they know, what their relative mixes of matrix ops and vector ops and memory bandwidth and such. If you have to support all the models that are out there, there's a very big variety and it shifts that provisioning, but especially memory bandwidth versus math in different ways. Particularly with the attention actually is starting to get pretty interesting. It started happening with DeepSeek when they came out with the MLA attention, and now a lot of the different models have different hybrid attention schemes with the alternate layers of 3 layers of state space and 1 layer of full n-squared attention. A lot of people are doing sparse attention, where they'll do a quick filter and then have to pick out the top K things to attend to. And this variation in attention, I think, drives a lot of different demands on the hardware. And so if you're in the position of being, we're going to be a silicon supplier, we're going to support all the models, it requires you to sort of look across all those models and say, what is the right hardware to build to make everybody as happy as you can without making anybody really unhappy? And that's a hard thing to do. You have to decide, which ones you're going to emphasize, which ones you're not. And as Norm pointed out, you've got to aim ahead of the duck, because it's going to be a couple years before this is out. In the meantime, a lot of clever ideas are going to be with the models that you haven't seen yet. So this is, I think, what good computer architecture is about, is figuring out how to make the most people happy and anticipate what the applications are going to need and deliver a product that serves them.
Yeah. And talking about models, I think one of the more disruptive things that's been recently developed is, it was proposed like 7 years ago, but mixtures of experts, because it requires a lot more interconnect bandwidth, and if you want to have quick responses for users, you really have to push down on the latency. So training is somewhat easier in that it's more of a bandwidth thing. Latency is harder to get in computer systems. Low latency than higher bandwidth.
Right, that's what drove the board fly configuration.
Exactly.
Latest GPU.
Yeah, I was giving at the Computer History Museum. I was struck at the Hot Chips conference. It felt like a recreation of the battles from the 1980s. So in the 1980s, when RISC processing became popular, people were using MIPS, millions of instructions per second, as the metric. And but that was up to you how to define it, like you ran all that stuff. So the RISC companies were saying, well, you can trust us, but all those other bastards are lying. So at Hot Chips, they were using tokens per second as the metric. And what were they running? How big was the model? No, it was just tokens per second. So there was an attempt to try and the solution for the RISC one led to the companies getting together, collaborating on benchmarks, which were called spec, which were pretty, there's pluses and minuses spec that they rallied around it, and then it turned out even if you were 10% slower, you could have other advantages. So that it worked out pretty well. So there was an attempt called MLPerf to anticipate this problem that's been around for many years. But I mean, and spec MLPerf was not quoted, was not mentioned, I think, at the hot chips. So do you agree that maybe MLPerf was not as successful a job as spec? And if not, why do you think it didn't? And I think it's your turn, Gail.
So I like MLPerf because it sort of gave a way of cutting through. It did what benchmarks are supposed to be. It's a very nice level playing field to cut through the BS and say, okay, how well do you really perform on this particular application? But I think it had two issues, which is why you didn't hear much about it at Hot Chips. The first is almost nobody submitted to it. And so
that's a problem.
because it was a lot of work, and we did every time. In fact, we did all the benchmarks, every generation, and every iteration of MLPerf was like 7.1 or something, or whatever. But a lot of startups would say, oh no, that's inconvenient. If we actually played by all the rules, we wouldn't look that good. So we're going to cherry pick this one result and put that on our slides and talk about that. So that's one reason why I think it hasn't really taken off. The other reason is, today what everybody is really worried about is tokens per watt or tokens per dollar. And there's really, most of the MLPerf benchmarks don't really address that. And even I think the one that comes close, it doesn't address it quite the right way. And so what everybody is showing, and actually you did see some slides of this at Hot Chips, is the semi-analysis inference X benchmark. Because it hits exactly the data that people want, and they do it in a very reproducible way. To get a data point on that semi-analysis chart, you have to have a, whether it's GitHub or Hugging Face, a repository of the code that you can load and run and show on that hardware with this model. This is the tokens per second tokens.
Is this something you run yourself, or they do it for you?
They do it.
And they run it on hardware, or is that how it works?
I can't remember the details of that, but it's
but that seems to be important. That's catching on.
But I think people are using inference X more than MLPerf today.
Yeah, that MLPerf does require like a full-time team. And
So it's
not as
expensive to run.
insignificant, and not a small team either. So, yeah, that's one of the issues with it.
So it ended up just being too intensive to run. Like the old TPC benchmarks were a big effort for these database companies. So expensive, and this alternative is working pretty well.
Yeah, it was both expensive and it didn't really give you the number you wanted.
It wasn't, okay. Other than that, it was great. All right, I'm supposed to warn the 80 people we'll do a poll after this. You'll show the poll results of my question after this question. Okay, so this is more open ended. The Silicon Gold Rush has had significant economic, societal, and even geopolitical implications. Beyond the technology itself, what do you believe are the most profound impacts of this rapid acceleration in AI hardware development, and what responsibility do hardware architects like us and leaders of these companies bear in shaping that future responsibly? Bill, I think it's your turn.
Okay. So I wouldn't call it the Silicon Gold Rush, I'd call it the AI Gold Rush, because it's really Russian AI. And I think it's really benefiting almost all aspects of our lives. So if you look at medicine, I think this is where one of its early applications was in image analysis, but now it's also being applied to diagnosis, where it's helping doctors get more accurate diagnoses, and we can have personal health coaches. It's sort of saying, look at us and say, I don't think you should eat that piece of cake for your calorie intake today.
That takes AI.
So what if you just ignored that coach?
Yeah, that's up to you. You gave these advice. In education, I'm a recovering educator. Every student can have a personalized tutor that really understands, what motivates them, how they learn, and presents material in a way that gets them through the difficulties of grasping complex concepts. In engineering, AI is already automating a lot of our tasks. I recently needed to design a piece of hardware. I basically wrote the spec and set Claude loose, and after fixing a couple errors in my spec, it came out with a pretty good design.
Did it fix this
No, it produced exactly what I asked for, which was not the right thing. We have to learn how to write a good spec. But it's basically enabling, engineers in all sorts of fields to move up the ladder, right? They're no longer doing the, junior level calculations and stuff. They're deciding what needs to get built. They're, managing a team of agent minions that, actually carry out the work. And a lot of business processes are moving in the same way. So we're all becoming much more productive. So I think in entertainment, it's helping us produce really, wonderful compositions, whether it's in movies or games or music. And so I think there's a tremendous number of benefits about AI. But on the flip side, any great technology can be used for good and it can be used for evil. And so the most obvious ones with AI are deep fakes. And I think we need to move very rapidly to embrace provenance and authentication, so that basically, unless you see an image as being authenticated appropriately, you just assume that it's fake. I think that there's danger with various nefarious uses. Cyber has gotten a lot of attention lately, although even though people like to talk about the AI side of cyber, the vast majority, I think it's like over 80% of all successful cyber attacks are human engineering. They're phishing. Of course, AI makes that better. You can use AI for pathogen design. And then there's the big risk is, as we make everybody more productive, the nature of employment is going to change, and we need more people in certain jobs and fewer people in other jobs. We need to find some way of easing that transition for people who are dropping out of one moving to the other.
Yeah, how do we reskill people? Norm, you got to take on this?
Yeah, I think one of the biggest impacts is going to be in science. They make a lot of super impressive results, which don't usually make the popular press. So with DeepMind, they folded all the proteins known to mankind.
And got a Nobel Prize.
Okay, yeah. And there's many other examples in science. So another thing is Google is using it in virtually all of their applications, but it's very subtle, and in many places you don't really notice it. So, for example, one of the first applications was Google Maps. That was when Louise was running Maps. And, the original Google Maps would say, drive, 1,000 feet and turn right on Tennyson Street, right? And by integrating the Street View database, now it says things like, drive 1,000 feet and turn right at Shell gas station. And that's much more accessible to people, and especially at night when the street signs aren't lit. Sunnyvale has nice lit up ones, but how often we don't. So there's a lot of subtle things like that, which I think people won't notice, but we'll just take for granted after.
Okay, let's see, can you show the poll? Does that work? Okay, so here's my question. The biggest bottleneck to continued widespread deployment of AI chips is energy availability, semiconductor manufacturing capacity, cooling of hot chips, memory capacity, bandwidth, cost of AI chips, don't know. Whoop. More people don't know. Okay, well, I guess we won't, it's still changing. But clearly, right now, it's energy availability. Well, maybe I should just, maybe I'll give it 30 seconds. So well, you guys can answer this question yourselves, and you can disagree with the audience. What do you think about what's the biggest limiter of those things?
Well, I was just going to talk about the energy availability.
Okay, go ahead.
So one of the issues is people are talking about gigawatt data centers or 5 gigawatt data centers. And the transmission lines are very hard to get permits for, and communities don't like to have big power lines running over their houses and such. And so a lot of the hyperscalers and other companies are moving to a model where they're doing on-site power generation. And you can do that in various ways. Some companies use natural gas to generate electricity, but if you put it in the right place, you can get most of the power from wind and solar. And so that's the approach that we're trying to take.
Which is carbon-free energy, and will not add to the load on the climate.
Right.
But by going off the grid and using carbon-free resources, you can build data centers without hovering things.
Yeah, you have an issue that you need steady power for your data center, and the sun is only out during the day when there are no clouds, and the wind only works when the wind's blowing. But in general, we've seen the various sources of supply being reasonably well balanced. I think it's just the natural market forces that are deploying resources to do that. But land, power, shell, which are some of the three things that you need, to build a data center, tends to drive that demand. And while a lot of people are looking at natural gas and co-locating generators, I think gas turbines are sold out for like the next 5 years because of this demand. And there are companies that are taking engines off of airplanes and converting them to be used as generators for stranding lots of passengers somewhere.
But if that's what we do, if we go to natural gas, we're going to have a giant carbon footprint. If we don't,
but it's often used to back some more renewable source. They'll have solar or wind, but because you can't count on that, and we don't have the storage capacity at this point, although there's some very good technologies that are.
And so you think like lithium batteries aren't going to be able to?
I think the lithium batteries are too expensive per kilowatt hour.
Even used
to ride through the kind of 20 to 100 hour thing you really need to bridge a gap when you might not have sunny days for a period of time. There are thermal batteries that are looking very promising, and there are people starting to build data centers with those that are cheap enough per kilowatt hour that they could fill that gap.
So if you're doing serving to consumers, then most consumers, there's a diurnal cycle, right? And so you don't have to have full power at 3 a.m. when you're serving. So
it has to do with keeping use of a capital resource, right? You spent $10 billion building a data center, and you'd like to have that capital resource be busy around the clock. And so if the consumers here are all sleeping, you'll sell those GPU cycles to the consumers on the other side of the world, where
the latency is too large.
Depends on use.
We like quick responses for our users.
What about nuclear is also carbon-free, and there's small modular reactors. I think Google's certainly made an announcement in this space. Do you guys have thoughts about nuclear as to help data centers?
We're looking at all technologies. Actually, the guy whose job it is to keep track of energy technologies and advise on data centers. And it looks promising, but it's always been expensive compared to what they call the levelized cost per kilowatt hour compared to natural gas. Natural gas is very tough to beat, and even if you're worried about the carbon, natural gas with carbon sequestration, I think still ends up beating nuclear on the levelized cost per kilowatt hour.
I'm a big fan of pumped hydro, but in Illinois, where I'm from, it's not too
flat.
Okay, now I'm going to go to the audience questions, just about when I said it. What are the biggest challenges, and the way the audience questions get voted up and down, so this is the most popular one. What are the biggest challenges to resolving the known supply chain barriers associated with AI hardware? Which I presume is the over demand compared to supply. So do you have a take on that? What's the biggest challenge? I guess, what's the biggest challenge?
The biggest challenge is it takes a long time to build a fab. And I think right now the place that's being felt the most painful is on the memory side. And the memory manufacturers are loving because they can charge many times more for the same part if they had them in plentiful supply. So maybe they're less motivated to build the fabs than what it would be. I think it's always this thing where you're trying to project demand, and when that demand exceeds what you projected, you've got this 2 or 3 year delay to actually build the production capacity.
If I had been paying more attention, I probably could have figured this out before it happened to some degree, because memory densities, DRAM scaling has stopped basically. And so since computers keep needing more and more memory, even ignoring the need for memory in AI, I think it's finally tipped the balance where for quite a while it'll be a better business. It used to be one of the worst businesses, DRAM manufacturing.
So, yeah, basically, you've already taught me that SRAM has already plateaued.
Yeah.
And, but DRAM is basically plateaued, but the demand hasn't plateaued.
Right.
And so it's gonna be a long time. Yeah, and I think it'll be interesting for the many companies, because their history is overbuilt fabs, and then the prices go down. They've got a couple of decades of that, and so are they just gonna say, we're highly profitable, what's wrong the way things are today, and just,
Unfortunately, competition hopefully will fix that. We're highly profitable, we'd like a little bit more share, so they'll build their fab up, and the other guys will too.
Yeah, but fabs are expensive.
Yeah.
And as you pointed out, take a long time, not only to build, but to get the yield up and all the other things.
I'm looking forward to what you guys are gonna say publicly about this next question. How significant will the impact of quantum computing be on the topics discussed this evening when that technology matures?
I would say very, very little. So I think quantum computing
I'm
is
so glad you're here.
is a great technology.
Bill Dally said that, not Dave Patterson. Okay, good, good. Yeah, so very little.
But the reason is there are sort of 2 really good quantum algorithms, right? One is to use quantum computing to simulate quantum chemistry, and the other is Shor's algorithm, which is to use quantum computing to basically factor the product of 2 large prime numbers and break a lot of modern cryptography. There's a third algorithm, Grover's algorithm, but for optimization, but it only gives you quadratic, not exponential speed up. But all of these algorithms have the property that they take advantage of the fact that quantum computers are large computation, small data machines. In people's wildest dreams, they'd like to get a few thousand error-corrected qubits. And then you get, from the exponential speed up of superposition, you get to do tremendous amounts of calculations on a few thousand bits. AI is the other way around. It's a large data, relatively small computation problem. So quantum computing is not going to have a measurable impact on either training or inference for AI.
I know who I'm gonna call on that. The question is, yeah, I mean, the AI revolution, we were 70 years into AI, right? And there was a lot of ideas that didn't work, right? It's been learned from data, the big data, machine learning, that's the breakthrough, and that's not like you said. So
Yeah, the area where it will have an effect is not on computation, I don't think, but communication. So the last Turing Award, or maybe the one before, I guess.
We need a Nobel. Turing Award for quantum? Oh, yeah, quantum Turing Award, you're right.
Yeah. Quantum transmission and cryptography.
But I thought the quantum transmission was very low latency and not much data. Is that right? Okay, that we're out of our, we're not this.
I mean, if you're sending 300-bit long keys, you don't need high bandwidth.
Yeah.
And then you can send all the rest of it encoded, and then it doesn't matter.
Your keys need to be longer than 300 bits.
This may be outside of our expertise, but that's the next question. What are the national security implications associated with AI hardware maturation? I guess if you've worked in stuff like that, Bill, do you have any?
I'm not sure I understand your question.
Okay, I think I don't know that one either. This is a specific company. I don't know if you're gonna. What is your take on etch architecture, essentially etching an LLM on the chip, or so like Alice or something like that?
Yeah, well, Callus would be the extreme, where they're playing to use ROM.
So these architectures are less programmable, and they're kind of building the model into the hardware, right?
My understanding is that And people can correct me if I'm wrong, but the company started out with that basis, and then it became more and more programmable, and now it's,
Is it they trying to make a product?
yeah.
Well, I thought I read something in the popular press that Google was building some chip that.
Would you like to reveal what he's seen?
There's research into everything.
Oh, that's a great answer.
But I think it's interesting because if you take the Talos approach, if you say, you know, they're going to the extreme. Not even that we're going to take a particular model and totally optimize for that, but we're going to take the set of weights and burn them into ROM because that will wind up being, you know, maybe 4 times as dense as SRAM, and way less dense than DRAM, by the way. You've got to have figured that there's some model that is not changing very fast. Because right now, you know, the frontier models are coming out with a new release every month or so. And even if you look at the various open source models, there's a clever new idea every couple of weeks that, you know, would completely break even trying to, you know, make it too closely matched to the model and make the weights programmable.
Yeah, I think this,
We're in the early days still. Programmability is critically important.
yeah, I mean, I think this is kind of what you said. This is a completely different universe from CPUs with million-line legacy code and millions of programmers. It's really small amount of code and not as many there, and the tremendous pressure to innovate. And so that's allowing us, that makes it easier not only for the hardware people, we see that the software people or the other people to innovate and deploy it. So it's a remarkable rate of change, and this idea that you could pick a model and get a chip out in time, and how long is that lifetime and stuff. It's an interesting bet, you know, be interesting to watch how it works. Okay, what is the right balance between centralized and distributed compute? What are the implications for edge compute hardware? Maybe we could just change that. You know, what do you get? You know, we all think about the data center.
Well, you know, we ship an awful lot of products that go into autonomous vehicles. Every Mercedes,
Sure,
well, a certain level has an NVIDIA processor and NVIDIA software in it for its self-driving features. And that's the example. If you can put it in the data center, you do, because it's much more economical to deliver compute in a data center for reasons of latency, or you have to be able to operate reliably with the network partition. You may need to compute on the edge, or in some cases, you're acquiring lots and lots of data. You can't afford to send it all the way back to the data center. You have to do some at the edge. But I think the general rule is if you can afford to do it in the data center, if one of those other factors doesn't limit you, you do it there. But if you have to do it on the edge, you do, and it drives a different set of requirements.
Yeah, and the Google Pixel phones have an edge GPU, so it handles a lot of stuff that's relatively simple, like speech recognition is pretty simple these days compared to these other big models. So, but if there's something that's too big for it, then it needs to go over the network.
Do you talk to the people who do the computers for Waymo? Are you familiar with that at all? Is that another part of the company?
They're, you know, they set up Google to be part of Alphabet, and then Waymo is deleted. So we don't, talk that much.
Okay. Since floating point precision achieves comparable AI results, will there ever be room for analog revenue systems?
Yeah,
You guys must hear this all the time. What about analog for, you can do multiply so coolly in analog, isn't that the future?
yeah, so one of the things that when you actually build real systems for a living, you have to do is test them to see whether they're right or not. And if you have something that's analog or, doesn't get the same result each time, it makes it really hard to test the device to see whether it's working correctly or not. I mean, if you're probing wafers, you have to send test sequences, and then you read back bits at tremendous speed, and they have to match. So analog, even if it can be more effective in some circumstances,
And so how do you know if the chip works or not?
Yeah.
Yeah, but even if you could test it, I've seen few cases where analog actually has an advantage. We continuously reevaluate this because it's a very seductive, argument that, oh, you want to do a matrix multiply, well, just, put, the activations in as, current, and then you have, a resistor, and if you get as a conductance, V is I times G, and you've got your matrix multiply for free, and by the way, you can then sum a lot of those together, also for free, and you wind up, getting sort of free computation. Well, it's not free. There's no such thing as a free lunch or a free multiply. It costs something, but what's even worse is, in analog, you don't really have a reliable way of storing a value. To store it for for a very short instant of time, you can put the value in a capacitor. But it's going to leak off, especially in modern semiconductor technologies. And if you need to move it any distance, it's very expensive to try to move it in analog. So typically what people do is they'll build a little array to do, in-memory compute analog, and do a matrix multiply of some activations times weights, and you sum the results and get the value out, and then you have to do an A to D conversion. And if you look at the fundamental requirements of energy, the A to D conversion, it winds up limiting you to something, if you wanted to be at, say, 8-bit precision, to something on the order of 5 teraops per watt, whereas with conventional digital technology, we can build accelerators over 100 teraops per watt. So you're down by more than the order of
So when you include the conversion burn, if you can do it without conversion,
you can stay analog, you could potentially make an attractive device. You have to convert it to lose.
Yeah, and I haven't been downstairs to the museum part lately, but it starts out with some analog computers, and there's a reason why they stopped being used around World War II.
this will, in addition to, the excitement around software tools and talking with your colleagues, a lot of excitement about using AI for hardware design. And so this question is, what will the next chip design software look like? Will it be radically different from what we have used for the last 3 years? This seems like one of you, both of you must have an opinion on this.
Yeah, so I think chip design software is going to be an LLM that you talk to. Say, I want.
Okay,
I want
very
this.
quotable.
I want this.
So we should sell my ECAD stock tomorrow.
They have a lot of expertise and a lot of the pieces that are needed to plug that together.
Okay, so you need to capture that knowledge in your LLM.
Yeah, and the LLM needs to know how to run the tools, right? You're going to need to run those tools to do, the place and route and verification. But I think, to me, I look at where we wind up spending a lot of the human time in designing a chip, and it's in verification.
Yes.
LLMs are really good at writing tests, right? You can say, make sure this works, cover all the edge cases, and it will write a whole test suite for you. And that's where 75% of our labor goes.
Yeah, I was going to say the same thing. It's the results we presented at Hot Chip showed, like 10% improvements in visual design and stuff. But design verification is the biggest part of the team is the DB team, and that they need all the help.
Yeah, we're seeing bigger than 10%. We're seeing, for average engineers, a doubling of productivity. And for really good engineers, 10x.
Well, what I was talking about was
Layouts.
basically performance.
Oh, okay.
But
You're talking about performance, not human productivity.
Yes.
So you're talking about for all tasks or for verification?
Yeah, I'm trying to remember the benchmark study that was for. It was for a particular task. The average came out to be about 3x. It made the engineers just way more productive. So I think that's going to be the design tools of the future. And there are a whole bunch of startups now. And again, this is the thing in AI. The real gold miners and people attacking a vertical. There are a whole bunch of startups attacking the EDA vertical.
Let me do one more. Yeah, I'm sure. What do you think about CPU, GPU ecosystem to make space for compute and memory or memory-bound workloads? What do you think about, how about making the CPU closer to the GPU? You must have a comment on that.
Well, Ours are pretty close, right? So they sit on what we call our, chip-to-chip NVLink. It's actually, technology internal we call GRS because it's ground reference. It's a single-ended, very high-speed link. And so you have to ask, what do you get by making them close? And we get a couple of things. One is we want to provision that link between the GPU and the CPU so that all of the, and I forget what it is, 1.8 terabyte per second of LPDDR5 bandwidth that's attached to the Vera CPU, and I don't memorize these numbers, that may be off, but all of that CPU memory bandwidth can be routed to either of the two GPUs that's attached to it. So the link is provisioned, so that link is never a bottleneck. Then the question is, what do you need in terms of weight? And because fetching from that memory isn't necessarily a relatively high latency operation, the little bit that you add with the link winds up not being that material. It's only a single link, you're not going through a switch or anything like that. And then there's control interactions, but if you think about it's basically when you launch a kernel that you need to do that. And that's, there's enough latency with the other parts of that making that link faster isn't that critical. It turns out we have many tens of little RISC-V CPUs on our GPU, but they're all there for little housekeeping operations that the user never sees. For the CPUs that the user programs, the NVLink chip-to-chip is actually just about as close as you want it. It's kind of the right balance.
How about for TPUs?
Yeah, so I think long term, the CPU that's associated with the accelerator is going to be doing mainly housekeeping and like babysitting the chores. I think the real interesting thing that's happening now is agentic computing. So if you say, write me a program, it's got to compile it somewhere, and you're not going to compile it with matrix multiplier systolic array, right? So you've got to have real CPUs with serious memory systems and stuff, and serious networking in the same data set.
Right, but in the data center, it doesn't have to be that close because you're firing off a cloud.
Right, but I think that's where the CPUs really will come in, is doing things like compiling.
Yeah.
Doing the tool calls.
Yeah.
It doesn't, but if you're going to do compiling tasks, I don't quite see why it has to be close to do that, because that's a pretty.
No, it doesn't have to be close, it's just in the same data set.
What I was going to do a closing question, but we have a suggestion as well, basically about advice to younger people. I was thinking like high school students, college students. One of the questions we have here, let's see if I can find it. I'm 10 years old. What advice do you have to me to prepare for my future? I think your kids are, all of our kids, I don't think any of us have, well, I have grandkids that old. What would you say to 10-year-olds? Do you have any advice to 10-year-olds? Then I'll ask you about older students.
So, study math and science. I think that you need a good foundation, and there's no substitute for having a really strong, background in mathematics and basic sciences.
How about you, Norman?
I think another important thing is communication skills are really important. So, learning how to write well. I know LLMs can do it for you. I think there's going to be cases where you don't have one handy and you still need to communicate well.
Yeah, I think we're going to do that. So, my last question is going to be, given the incredible pace of innovation we're witnessing, what advice would each of you offer to young computer architects and engineers entering the field today looking to make their mark in the computer architecture space? You guys have certainly made great marks in your careers. As you look back, what let you make those marks, and what do you think you should offer? What advice would you give for this current generation?
Well, I think the world's very different today. I had great fun early in my career. I designed a machine at Bell Labs, drawing all the circuits with pencil on vellum, having a technician who did the layout for them. And it actually all worked on first silicon without ever doing a simulation. But having great manual logic design skills, I think no longer has any value.
I know a lot about punch cards.
Yeah. I think I would have 3 pieces of advice for an aspiring computer architect. The first is to master a vertical. The second is to be very broad in your understanding of computer technology. And then the third is to make AI your partner. And I think, the reason for the first is I think a lot of the value today is in understanding what to design, not having great manual logic design skills to realize, because the tools will help you. The AI will help you realize that making AI your partner. But then I see many computer architects who limit themselves because they'll ask the memory guy, oh, can we build a memory like this? And they'll say, no, you can't do that. But if you have a really broad understanding of circuit design, you realize he's not thinking enough out of the box. You can build a memory that does that. This machine at Bell Labs, by the way, had a 3 TB RAM on it.
Wow.
All the circuit guys told me, oh, that's not going to work. And I went and I prototyped it up and convinced myself that it would work. We actually did a test check before we did the final check to make sure it would. But you have to be broad enough in your understanding that you can do circuit design when needed and things like that to sort of get outside the box, get outside the limits of the conventional thinking of what the toolbox you have available to you. And then I think people really need to figure out what is the uniquely human part of the human AI partnership in doing computer architecture, and practice of being good at what the human can do, because there's no point in doing what the AI can do. It's just going to do it better.
But you have to be able to, so far you have to be able to recognize when it's screwed up, right?
Oh, yeah.
So do you have to know how to do it manually to be able to recognize when it's
I can definitely recognize when it's screwing up. Maybe that's because I can do it manually.
Yeah, well, yeah.
The other thing you can do is you can get one AI to check the other one.
Okay. How about you, Norm? Advice to the next generation?
Yeah. For computer architects, it's got a long history, going back 70 years and more. And there are a lot of lessons learned along the way. And I think, one of the best things to do is just learn about all those historical lessons, because some of them apply today, some don't apply today. And there's no point like reinventing something that didn't work the last 7 or 8 times.
Okay, with that, I think we invite Mark back up on the stage.
What a great conversation. Let's give it one more round of applause. When you think about it, we are called the Computer History Museum, but our conversations really are about the past, present, and future. And so that's really what the museum is about. We would love to get your feedback on tonight's program, so you can scan that QR code. Please tell us, it helps us plan other events. The other thing you can use for a QR code is help us out here. We are reliant on your donations as a museum. A lot of people think that it is Google and NVIDIA, that is the big companies that support us. It's actually all of you. So thank you guys who are supporters. If you're not a member, we encourage you to join. We really appreciate all the help that you can give us. That funding will help us put on our next event, which is Boris Cherney from Claude Code. So it's the flip side of what you guys are talking about. So if you enjoyed tonight, I think you're really going to enjoy hearing Boris speak about Claude Code. So thank you all for coming. Thank you for your questions. Thank you, Mark and Mary Stevens, for your support tonight. And have a safe drive home. And thank you for